I want you to imagine a situation where, as we get closer to a cell phone tower, our cell phone gets better and better signal. Now, this would make sense because cell phone towers are emitting a certain amount of energy. As we get really close, then we're able to get more of that energy to our phone, and we could imagine we get a better and better signal. And as we get super, super close, well, we'd expect to get an increasingly better signal. Does that ever stop? Or does it just kind of explode into a forever perfect call where I have super human type hearing and can hear even the grass on the other end of the line? Okay, the model maybe falls a little bit short. Okay, let me give you another situation. What about I'm in a business, I'm selling product, but for some reason my sales have been going down. Now, my boss really wants to make sure that I'm bringing in the same amount of money every single month. So if my sales are going down, what do I need to do with my price? I probably need to raise it so that everything I sell is worth more and more to the company. But if I do that, then I'll start to sell less. And if I sell less, I'll raise the price more. Does that ever end? Do I eventually have to just charge people an inordinate amount of money? The first person to buy a product has to make up for the entire month's rent if it's the only sale I have? These ideas of saying that you're trying to kind of grow forever large, or that if we look at it the other way, as I move away from the cell phone tower or I start to sell lots of things, every person has to pay less and less, or the signal reception becomes worse and worse. These are ideas of really kind of tracking towards models, tracking towards really big things, really small things as we move across our story. And I want to show you how we can represent all of these ideas using rational functions. And these are very, very common ideas. Their rational functions are used from everywhere from business to physics all the time. They're used to model black holes. They're used to model economics as a large. They're incredibly useful things. And they come from exactly where their name would suggest. These rational functions, well, this rational, as we know in math, this rational just simply means ratio null. So this is a ratio null number, which means that it's a fraction. It's a fraction, but specifically it's a fraction that I am creating with polynomials. It's a polynomial fraction. So it's a polynomial fraction that I'm making into a function. Okay, let's look at how some of these graphs might look. If we interpret things as a story, it often gives us a lot more insight than if we just try to brute force things with the symbols or with the plugging in numbers. If we try the traditional algebra, these are stories, these are models. Let's try to interpret them. So the first thing I want us to do is just kind of take a moment, look at this and say, which of these would you rather graph? If you had to pick one of them, what looks the least intimidating? I'll tell you my thoughts. This one here, no idea what to do besides plug in numbers. This one right here, no idea what to plug in besides numbers. I know it looks like a parabola. This part looks like a parabola with a little something extra. Okay, this part here at least has some interesting x values. I mean, x value of 1 and x value of -3 catch my eye. X value of 2 catch my eye. This part right here, maybe there's some numbers that kind of catch my eye. Maybe like -3, or +1, +2. We could play around with some of those values. But let's. I'm gonna choose this one, I think. So, what are the interesting values? Or what's the story I'm looking at? I've got a parabola, something that looks like a parabola, and then a little something extra. And I do say a little something extra because here's what I'm thinking about. If I plugged in some numbers like 5,000, then I could read this off as a story. So, I don't know, let's do something like if I put in -5,000, and I'll divvy this up, -5,000 would get me something along the lines of whatever a parabola would be at 5,000. So it'd be a parabola plus 12 divided by -5,000-ish. So that'd be 12 divided by a very small number. So that'd be a small negative number. So we'll say minus something small. And I'll change that to a minus. So I'll say, so it's a parabola minus something that's small. Okay, well then that gives me a pretty good idea. It's pretty close to the parabola. Should I just draw the parabola as a reference? Let's just do that. Let's give us some things that we could play around with in the picture. I don't know what I'm doing here. I'm just playing around. But playing around sometimes leaves us with some cool ideas. What would the parabola have been? The parabola would have been a parabola with zeros at a +1 and -3. -1, 2, and 3 right here. And I know that because if I plug in 1, I would zero out one of them. And if I plugged in -3, I'd zero out the other. So those are my zeros, 1 and -3. I know it's going to have an axis of symmetry. It always looks like a U shape. It's always facing up or down. So that's going to be halfway between my zeros, and halfway between my zeros would be right here. So somewhere here, I've got an axis of symmetry in my parabola. And I could just find out what happens if I plug in -1 into my function here. So let's do that. We'll show our work. This was -3 when we plugged it in. We said got 0 plus, I don't know, a little 12 divided by 1. No, -3. 12 divided by -5. There it is. So again, something that's just about -12 fifths, something that's a small negative number. Okay, then we plugged in, we said what happens if I plug in -1? If I plug in -1 to all of this, this would be -2 times 2 plus my extra, or I guess minus my extra probably, minus my extra. So that gets us something that's just about at -4. So in my reference parabola, I'll put this at -4. -1, 2, 3, and 4. Let's scrunch this up. Let's make each of these worth 2, I think. We'll do -2, -4, -6. Okay, so there we have it. -4 with a little something extra. So we've got our reference parabola like this. But this isn't my graph, this is just a reference parabola. We're just playing around. Okay, we still have to take account of this little bit that's extra here. Well, I don't want to go through the trouble of dealing with all of those fractions. I mean, how can I just interpret this as a story? Well, as we said, if I'm looking at getting numbers that are getting really, really big towards the negative, I'm going to be just a little bit below my parabola. Okay, well then let's just draw a graph that's a little bit below the parabola. That seems fine. As we look at numbers that are getting really, really big, like positive 5,000, shouldn't we be getting things that are like our parabola plus a little bit extra? So if I was graphing that in, wouldn't that be something that if I extend this way, I would be getting something that is just a little bit over my parabola? Interesting. What other x values do we have? Well, we know that this is going to blow up at x equals 2, right? Because if I tried to plug in 2, that's going to be 2 minus 1 is 1, 2 plus 3 is 5, plus 12 divided by 0. That's going to be something that explodes. That's a vertical asymptote. I could put that into my sketch here. I could say there's going to be a vertical asymptote right here that causes this entire thing to explode. And in fact, I think that's about all that we need. I mean, take a look at the story that I'm crafting in my head. I'm a little bit below my parabola as I go off towards the negative. As I come in close, I'm hugging in that parabola close, but then I eventually need to explode for that vertical asymptote while still being underneath my parabola. And on the other side, I am coming in from that explosion above the parabola, and then I cut in really close to it as we go along. So it's like I'm being an artist here. I'm really just kind of sketching in some construction lines, and then I can take them away to get a better idea of exactly what my graph was. It wasn't exactly the parabola, so I'll get rid of all of the parabola stuff I had originally, but it was something that looked pretty close, and that's not a bad sketch. And there we have it. So we don't exactly know these points, but we have a pretty good sketch that is going to be something that's pretty close to that parabola, the parabola that we had sketched on in. So it's like I'm approaching this thing as an asymptote. And an asymptote is something that we approach forever closely, but we don't actually get onto. It's like a reference line when we're trying to draw something constructively. So in fact, any of these ones that you had chosen up here were actually the exact same structure, but the one that we had that showed the most interesting x values was very helpful for us in drawing our picture. So what I'd like you to consider is, could you actually have made these all look like each other? Like, I'll try this one out for us. Let's do x cubed minus 7x plus 18 divided by x minus 2. Now, there's a bunch of different ways that we know to do this. We know the polynomial long division way, which is where I have x cubed minus 7x plus 18. And I'm trying to divide that by x minus 2. So I'm looking for how many groups of x are there in x cubed. And I would say, oh, there are x squared of them. So x squared times x cubed is right there. And then I would say, oh, we need to make sure that we put our placeholders in. So let's put our placeholders in. We'll move that on over here. And we'll add in our placeholders, 0x squared. So x squared times x gets me x cubed. X squared times negative 2 gets me negative 2x squared. I'm going to take all of these things away since I just accounted for their groups, which really means that I'm adding in the opposite. and that gets me 2x squared, and I haven't yet divvied up my negative 7x. I could then, again, how many groups do I have? We could look at this as saying I have plus 2x, that'd be 2x squared, minus 4x that I'm about to take away with that. I'll subtract that, which is just the same thing as adding in the opposite. That leaves us with 3x, negative 3x, and 18 that I still need to divvy up. And we'd say, okay, that's going to be negative 3 groups I see. Negative 3 times x gets me negative 3x, and then negative 3 times negative 2 gets me a positive 6 with this 18 that I carried down. I'm going to take that away, which really just means add the opposite. And that's going to leave us with our 12 as a remainder. So I have, as we see up here, x squared plus 2x minus 3 with 12 divided by x minus 2. 12 that remain that still need to be divided by x minus 2. So that's a great way of looking at it. I want us to really quickly see another way that I think I prefer to organize this all in. And I like to refer to this as, let's say, long edge division. And I'll show you why that is in just a moment. We'll put our answer down there. And so I like to draw this division bar, but with a very long edge. And what we're going to be trying to do is long division, but I like to think of this in terms of grouping. And I find this to be a lot more intuitive. So I'm looking for groups of x minus 2 in my x cubed minus 7x plus 18. Now we could say, okay, well, how many groups do you think you see? How many groups of x minus 2 do you think you see in here? And maybe we say that I see, I don't know, x squared groups of x minus 2. No problem. That would be that you are about to take away x cubed and then the opposite of 2x squared. So you're about to take away all of this. Okay, well then let's take it away. Let's take away our x cubed. Let's take away our negative 2x's. That would be the same as adding 2x squares. Okay, so let's take that away. What are we left with? This takes everything away. I've accounted for it in my groups right here. And I still have 2x squareds left over. And I bring down my negative 7x. Okay, well, and my 18, because I haven't grouped those away yet. So I found this many groups. I took some things away as a result. Excellent. Now how many groups do we see? We see maybe 2x groups of x minus 2. Okay, well, that would account for 2x squared minus 4x of these amount. So, okay, let's take that away. Let's take away our 2x squared. Let's take away our 4x. Which is the same thing, or take away our negative 4x, which is the same thing as adding 4x. Okay, no problem. What's that going to get us? That's going to take all this away. Negative 7x and 4x gets me negative 3x, and we still have 18 things that I haven't accounted for. All right, how many more groups do we see? Well, maybe the next thing I see is I see the opposite of 3 groups, right, in this thing, because if I multiply that by x minus 2, that would get me negative 3x plus 6 that I'm accounting for. So let's take that away. Take away the negative 3 was the same thing as adding 3x, and taking away 6 is taking away 6. That's going to get us where we are left with 12 as a remainder. And so all in all, what we have is we had one of these x squared groups. We had 2 x's. We had negative 3 groups, and we had a remainder. We still had 12 left over at the end of the process, where 12 still needed to be divided by x minus 2. And that's exactly how we start to see the process of looking through problems that maybe look like this, and we start getting them closer to something that it is that we can graph. All right, so we see from here that we should be able to take these expressions that we're kind of breaking down and use all the tools we've been playing with so far to say, well, what can I do to make this easier to graph? And as we've recognized, this is nothing more than a quadratic. So I can actually put this into my 4 quadrants. I can look at this and say, okay, this is where my x squared goes. This is where my negative 3 goes. And sure enough, if I think about things that multiply to x squared, that'd be x and x. Things that multiply to negative 3 is going to be negative 3 and 1 or positive 3 and 1. And after a little bit of play, since we're looking for things that multiply to negative 3 but add to 2, that's going to be a positive 3 here, which gets me my 3x, and a negative 1 here, which gets me my negative x. So that sure enough, I can look at this entire thing as being just x plus 3 times x minus 1. So what if I wanted to take these things and put them back onto the top of the fraction? I mean, after all I'm looking at this is the difference here being that I have this thing not in a fraction and everything over here in a fraction. Well, then let's just put it in a fraction. X plus 3 times x minus 1. And then if I wanted to put it over x minus 2, I would need to make sure I multiplied by it as well as divided by it. And I could add that to 12 over x minus 2, and sure enough, we can get a common fraction using that common denominator. That gets us right up here. Well, what about this last one? This last one here, again, we could make this all look simpler by just simply doing a few of those rectangle diagrams. I can do x plus 3 times x minus 1 and just multiply that on through. That's x squared plus 3x minus 3, which would be x squared plus 2x minus 3. That'd be the first two multiplied by each other. I'd still have the x minus 2, and I'd still have the plus 12 all over x minus 2. But sure enough, this here is just another rectangle. Do you see it? This is a x squared plus 2x minus 3 by x minus 2 rectangle. So we could again just multiply this all on through. This will get us x cubed plus 2x squared minus 3x minus 2x squared minus 4x plus 6. And if you simplify all this up, you're going to see we have 1x cubed. We have no x squares. They're going to cancel away. We have the opposite of 7x's and a 6. So we carry along those 12, and we still have to divide by x minus 2, but after you combine the 6 and the 12, you're back up to where you started. So we can use all the different tools we've been practicing in this class to rearrange our perspective to find things that are easier or harder to work with. So how would we graph some of the following ones? First things first, we understand that looking at them in this structure is not going to be as helpful as if we can look at them after doing some division and say, okay, it's going to be close to something else easier, with some minor adjustments, and then maybe we'll do some factoring to help find some even more interesting x value points. So what do we have for our domain? Here we know that we're going to have a trouble when x is equal to 1, because if x is equal to 1, the denominator is going to have a divide by 0 error. So we'll keep in mind that that's going to correspond with possibly a vertical asymptote, but we'll let the division show us how that is. So what do I like to do in the division? I'm going to do the long edge division method that I kind of previewed to earlier, because it helps me to expand out my thoughts. So I'm going to do x minus 1, and I'm looking for groups of x minus 1 inside of my 2x cubed, my 3x squared, my minus 2x, and my minus 2. And there's everything accounted for. I don't need to put any placeholders in here. So from here on in, it's just me trying to find ways to find these groups. So let's start at the beginning in the same way that we would if we were trying to do this with our dot division. In fact, actually, let's do a real quick callback to that dot division so we can follow it through in the exact same way. What we are doing here is we have the opposite of two groups, opposite of two blocks. So we can think of this as two anti-dots in our ones category. In our x's, we have two anti-dots. And then in my x squares, I have 3 regular x squares, so not the opposite of anything, just the regular amount. And then I have 2 x cubes right here, so 2 x cubes. And we're looking for groups of this x minus 1. This would be like a dot next to an antidot. This is what we're trying to create. So how do we make that happen? Well, in this first situation, as I'm trying to find things that group with my x cubed, I need those antidots afterwards to partner. So I can create an antidot and even another antidot if I keep the meaning the same. So that means that I'm creating a dot and a dot. Really, what we can think of this as is saying that I've just added negative 2 x squares, and I've balanced that with 2 more x squares. So it's like I've changed the appearance, but I haven't changed the meaning. But that would allow me to say, okay, here you go. This would allow me to grab one of these as one group, and I could grab the other one as another group. So that would be 2 groups. And then similarly, we could start to create things in that X category. And so that would be, okay, well, how many do I need to partner up with these 1, 2, 3, 4, 5 regular dots? I would need 5 anti-dots. I already have 2. Let's make 3 more, 1, 2, and 3. And to create those 3, I need to keep track of the fact that I kind of had to add 3 to keep the meaning the same. But then again, how many is that going to get us? That's going to get us, let's see, I'll make this one pink over here. That's going to get us 1, let's see, 1 group, 2 groups, 3 groups, 4 groups, and 5 groups. So we could mark that in. So far we've been able to create 2 groups in my x squares. I've been able to create 5 groups in my x's, and then I would be trying to find out groups in this next one. So I'd be looking to find groups. My groups would be, when I am trying to find, again, one of these dots to partner with one of these antidots. And so that would be a group right here, a group right here. And then I would have, let's see, I'd probably want one more So I could again create one more antidot to finish this off, and that would leave me with one dot. That's going to be that I have officially found another group of my x minus 1s, and I have one left over. So sure enough, what I'm going to be expecting to get when I finish this entire thing in my long edge division is I should have 3 groups in my 1s. I should have 5 groups in my x's. I should have 2 groups in my x squares, and I should have 1 left over. So it'd be with a remainder of 1. In other words, I'm expecting to get 2x squared groups, 5x groups, 3 1 groups, and have one thing that still needs to be divided by x minus 1. Let's check that in our long edge division. So first things first, let's do it with how many groups do I think I'm going to see in here? I think I'm going to see, of my x minus 1, I think I'm going to find 2 x squared groups of my x minus 1 because I'm focusing on this first term right here. I'm just trying to match that one and make those dots go away. So sure enough, that's going to take away 2x cubed minus 2x squared. And so let's take that away. Minus 2x cubed minus a negative 2x squared is going to be minus a negative 2x squared. And if we add all that together, this cancels away. We're left with 5x squared. On the next one down, we still have the minus 2x and the minus 2 that I haven't grouped away yet. So we could say, how many groups are going of x minus 1 do I think I have left? And we could just make a guess of that. Maybe 5x, because 5x times my x minus 1 looks like it's going to get me that leading term, that 5x squared minus 5x. And sure enough, if I take all that away, that'd be like taking away my 5x squared minus 5x, which taking away really just means add the opposite here, and that's going to be leaving me with 3x and a minus 2 that I still haven't grouped away. So we'd say, okay, how many more groups can I find of my x minus 1? And we could say, well, maybe I find that this would be, I don't know, maybe I have found that this would be 3 groups in this, because that would, again, focus on that leading term. That leading term would give me 3x minus 3, and if I take all that away, that's taking away 3x minus 3, which is really just adding the opposite. Adding the opposite is going to give us 1 left over, and we see that we've got exactly what I had happening up there in the dot division. I have 2 groups, 2x squared groups, and then I have 5x groups, and then I have 3 1 groups, and I have one thing left over that still needs to be divided by x minus 1. Wonderful. Now I'm running out of a little bit of space here, but we could go through, again, trying to find a way to organize this entire thing in order to get an even better estimation of how to plot this. So like, for example, let's actually try to factor one step more how to do this 2x squared plus 5x plus 3. Well, my 2x squared goes up here if I use the area model, and I could put my 3 down here, and I could ask myself, okay, what multiplies to 6 and is going to add to 5? That would be 2x here and 3x here. And lo and behold, I would be able to write this entire thing as 2x, x, this right here would be 1, this right here would be 3, and we could write this entire thing one step more simply as an x plus 1 by 2x plus 3 plus 1 over x minus 1. So now it's a parabola with a couple of interesting points in a vertical asymptote. Okay, let's go down to where we can actually sketch this now. So important points. We've got this entire equation can be thought of as x plus 1 times 2x plus 3 plus 1 over x minus 1. Okay, so let's think about what happens if we go really big. So let's do a little bit of a table here. We've got x, we've got f of x. If I plug in something like negative 5,000, negative 500, that's going to be what? A parabola plus 1 over something negative. So that's actually going to be a little bit, that's going to be a negative number. That's actually going to be a little bit under a parabola. So it's going to be parabola minus the extra, right? And we could say, what if I put in positive 500? Positive 500 is going to be parabola plus a little bit more. So parabola plus a little extra. And I could say, okay, what happens at each of these interesting numbers? I already know this is going to be a 0 at negative 1. This is going to be a 0 somewhere else. Let's start plotting these points. So first thing first, we now know that I have a 0. I'm going to 0 out at negative 1, so I can put that in. Negative 1 is going to be an interesting point. And also negative 3 halves is going to be an interesting point. So let's actually write this in order. Negative 3 halves is going to be a place where you get your 0 minus a little bit. And then over here, you're going to have minus 1 is going to be your 0 minus a little bit. And then I know when I get to 1, that's going to be a place when I am on the, that's my undefined, that's going to be my vertical asymptote. So now I should be able to sketch all this out. Let's go ahead and put this in. Since it looks like it's going to be quite crunched around here, we'll make these tick marks half increments. So this will be 1/2, this will be 1, this will make this 2. So we'll go 1, 2, every half increment should be fine. And we'll do the same thing over here, make this go up so that it's every half increment. So this is going to be 1 or -1. Next one's going to be -2, and we can start to plot our interesting points. So first, let's do our parabola, our reference parabola. I'll do that in blue. So we'll do it with a dotted line so it doesn't get confusing. The first thing is I'm going to plot my 0, which is at this kind of -1. I'll do a little open circle there because it doesn't actually exist there. It's just a little reference for me. And then I've got the next one at -3/2, so it's going to be right here. Okay, so a really skinny parabola. I know that halfway between them, I've got an axis of symmetry. And so halfway between -3/2 and my -1, I know that's going to be what? -1 1/4. So, okay, let's see what happens when I plug that in. -1 1/4 would be -5/4. And if that feels a little bit weird, we can actually just think about how that would happen. That would happen as I put down here by saying, okay, we're just averaging the two. We're doing -1 plus your -3/2 and finding that midpoint between them, which is our -5/4. Okay, when you plug all of that in, what do we get? -5/4 plus 1 would be 1/4 or -1/4 times plugging -5/4 into 2x plus 3 gets us, oh golly, -10/4, which then I would add 12/4, that'd give me 2/4. So I think all in all, this is going to be a very small negative number. All right, so I'll plot in just a little small number here, and that should give us enough to kind of sketch out this reference parabola that we have going on. So here's my reference parabola with its axis of symmetry, and now I'm going to try to fit in everything else with just a story. So the story says that I start a little bit below it, I end a little bit above it, I have a vertical asymptote over here at x = 1, so I'm going to try to sketch that in as saying I have a vertical asymptote. Oh, maybe I need to shrink everything down. I need to shrink everything down so that it becomes a little bit wider. Okay, so we're just sketching, we're resketching, we're going back and changing this again. So now I'm going to try to increase that Y scale so that I kind of flatten my parabola. I can get a better view of what's happening. So that would be, I need this thing to kind of be a little bit wider. It's going to scoop down just a little bit, be a little bit wider. And I need to start from underneath it. Okay, let's try this way. I start from underneath it. I scoop in close to the parabola until I come in close to my vertical asymptote. That causes me to explode downwards. And then over here, I start from above my parabola, coming back from that explosion and tracing along next to it. Okay, and that actually looks like a pretty decent graph. We're just looking at the pink that's right there. And if you want, you can remove some of those construction lines, or at least a few of them. I like to leave a few just so I can kind of go back and double check my work later. But that's exactly what we're doing. It's something that looks like it's hugging a parabola. Now, I've got it plotted in GeoGebra so we can actually see what's been happening behind the scenes. And I'll show you in a little bit of a story arc. So here is, again, that exact same thing. You can see that it's exactly like we might have thought about. There's a vertical asymptote right here at x = 1. It's actually really close to the parabola without the little something extra. And the orange is the original, like we've got the green, which is the original function, which is right on top of the orange. That's why it looks a little bit brown. But that's exactly what we're talking about. That's the exact same thing. So we started with this one. We made it look a little bit different, but it kept the exact same meaning. And then we interpreted some important information. It's going to touch down here at these values right in here. It's going to follow a parabola arc pretty closely, except for at your vertical asymptote where it's going to cut off dramatically. All right, so let's try this problem out here. Now, again, these are difficult problems. For me, when I was making this video, there was a bunch of times I had to pause and recheck and rewind. So if you feel like you're having trouble with some of these, that's okay. Find a partner to work with and call me over in class. I'd be happy to help explain some of these answers to you. So, but we can absolutely understand where they're coming from at the very least, so we can participate well in those discussions. So if we're looking again to figure out where the domain is restricted, we need to look for the places where we're going to have some trouble. And so here, obviously the denominator can't be equal to 0. So it's going to get us negative 2x squared cannot be equal to negative 1. That means that x squared cannot be equal to 1/2. And when you square root both sides, remember that we don't want to just square root, we have to do a plus or minus square root to get rid of that full x squared. So if we do a plus or minus square root on both sides, what we're going to get is that x is equal to, 1 over this plus or minus square root of 1/2. That'd be 1 over the square root of 2. Oh, but we're much more commonly seeing that as plus or minus root 2 over 2. Okay, that one's a little bit tricky, and that one actually caught me up before. So those are going to be where our vertical asymptotes are. How can we do the division for this to make it look like something simpler? Well, we could look at it as, let's do, instead of 1 minus 2x squared, let's put it in standard form. We'll do it in the decreasing power order. So negative 2x squared plus 1, and then we'll do our division, and our division is going to be for that 4x squared minus x plus 1. I'm looking for any placeholders I might need to put in, but I don't think we do. Let's make sure that I make this negative 4. It looks like a negative 4. Okay, negative 4x squared. And let's start to do our division. We're looking for groups of our negative 2x squared plus 1. Where can I find these groups? Well, maybe I can find 2 opposite groups in just my units, and that would get me 4x squared minus 2. And remember, if any of this feels weird, go back and do your dot diagram. It'll pop right out. So we're trying to take this all away. We're going to take away the dots that we've already accounted for, take away the negative, or this 4x squared minus 2. Taking away is just adding the opposite of it. And so this allows us to see that what we're doing is we have negative x plus 3 left over. I don't think we're going to find any more groups of this x squared because we're already down into the x area. So sure enough, what's our final answer going to be? Our final answer is going to be that I have negative 2 and a negative x plus 3 that still needs to be divided by negative 2x squared plus 1. Okay, well, let's start to, again, let's sketch this entire thing out. Now we have a nice little reference line. So what is our reference line going to be? I know that I can plot my axes here. I know that I am looking for something that has a reference at negative 2, so I guess I can kind of plot that in. I'll put negative 2 right here, negative 1, negative 2. And I'll draw in that horizontal asymptote at negative 2. Okay, what happens as we get really far one way or another? Oh, also I have my vertical asymptotes. Let's not forget about those. Plus or minus root 2 over 2 is a little bit smaller than 1, so maybe I'll make this out here be 1, and this out here will be negative 1, so that I have vertical asymptotes just about at my negative and positive root 2 over 2. You plug in your calculator, that's going to be about negative 0.707 and positive 0.707. So we got those well placed. Good. Let's talk about our story. If I put in very large x values into this, what's going to happen? Positive x values are going to give me something negative on top divided by something negative on the bottom. So that's going to be negative 2 plus a little extra. I'm going to end a little bit above this diagram. No problem. What if I put in some negative values? The negative values are going to get me a positive thing on top and a negative thing on the bottom. So it's going to be a little bit under. So we're going to end a little bit under this graph. What other information do we need? Well, we would need to say, I don't know, maybe are there any zeros? Are there any times when this whole thing up here could be equal to 0? That'd be interesting. We could try to factor it. If we tried to factor it, we'd be looking for ways to factor 4x squared plus 1. I could put that in the bottom of my little factor rectangle here and try to think about what that would be. No, I'm not seeing anything that's going to multiply to 4 and add to my negative 1. Okay, we could try quadratic formula. So I could look at the quadratic formula and I could say, okay, that'd be opposite of b plus or minus the square root of b squared, which would be negative 1 squared, minus 4 times a times c, which would be times 1, all over 2a. That'd be 2 times 4. But if you actually look at this one real carefully, we can see inside the square root, I'm about to do 1 minus 16, and that's going to give me a negative number. So actually, there are no zeros. Okay, so there's no zeros. Interesting. Okay, so that means that this negative graph can't come up towards this vertical asymptote, it would cross at 0. Instead, it needs to go swoop down here. That's really interesting. This one here, again, can't swoop up because it would cross 0. It has to swoop down here. Okay, so we're starting to get a little bit of a structure here. We just need to figure out what happens in between. Well, if there are no zeros and I've already got my vertical asymptotes accounted for, then just like we did with our number line we have identified everywhere on here between negative root 2 over 2 and positive root 2 over 2. We know that this area has got to be negative all the time, else it would have crossed 0. This place has to be negative all the time, else it would have crossed 0. We can just choose one representative point, one test point in here, like if I plug in 0. So let's try to plug in 0 into the original thing. If I plug 0 into the original thing, that's going to be 4 times 0 squared minus 0 plus 1 divided by 1 minus 2 times 0 squared. And I think all that's going to simplify out to just, 1 divided by 1, so it means it has to be positive in the middle. Somewhere over here it has to be positive and never cross. So that means I must kind of swoop down and swoop back up. And I think we've got our entire graph. In fact, if we put it into GeoGebra, what we can see is actually exactly what we were just playing around with. I'll pull it on over right now. What we have is, and I'll make it look like the full story, we started with our original. It looks just like this. We made it look a little bit different, and so sure enough, you can see that it just darkens the original thing. I haven't changed the picture, I've just changed the appearance of the equation. We found our vertical asymptote at the square root of 1/2, which we call root 2 over 2, the negative square root of 1/2, which we call negative root 2 over 2, and sure enough, we have this horizontal asymptote at y equals negative 2, and that's going to be exactly where we hug towards the end. That's very, very nice. So we can get really complicated graphs pretty quickly by just running through all the tools we have in our head. Okay, let's do this last one together. So this last one here, I have x divided by x squared minus 4. I'm not going to do any division for this one because I've already got it where the numerator is smaller than the denominator. If I try to do division, I'm not going to find any of those groups. So instead, I'm just going to begin sketching out. I'll maybe make reference to the fact that the denominator here cannot be equal to 0. Which means that x squared cannot be equal to 4, which means that x cannot be equal to plus or minus 2. So we've immediately got, if I'll put negative 2 there, or negative 2 here and positive 2 here, these are going to be my vertical asymptotes. I can imagine what's going to happen if I plug in really large numbers. If I plug in a really large positive number, it's going to be a positive number divided by a big positive number minus 4 is still a big positive number. So it's going to be positive over here. So it's going to be as if I'm getting close to... Ooh, actually, that's a good question. What am I getting close to? What is the thing that I could put in front of all this to give me a reference line? What about 0 plus x divided by x squared minus 4? I'm getting closer and closer to 0, which makes sense because as I get bigger and bigger numbers, the denominator is going to get huge. I'm going to be dividing by bigger and bigger numbers. Okay, now we have everything we need for our story. So I'm going to be a little bit above 0 as I go off this way. If I put in negative numbers, that's going to be a negative amount there. So I'm going to be a little bit below 0 off this way. Do I have any times where I am 0? It looks like I am 0 at x equals 0. So I can plot a point at x equals 0. Y is going to be equal to 0. And then we can really kind of say, okay, well, what do I have between that? This has to swoop down. It's my only time. This one has to swoop up. It's the only way I can get it without another 0. Between them, let's plug in some values. We'll do some test points. So we can say over here now, between negative 2 and 0 and 2, we'll plug in positive 1. That's going to get me 1 over negative 3. So that's a negative value. I'm somewhere down here. And if I plug in something that's 1 over 1 minus 3 is also 1. Oh, sorry, this should have been negative 1 over negative. This would have been a positive value. Okay, positive value. Then if I plug in the positive one, it becomes a negative value for my f of x. And sure enough, what we're going to see is that it's going to cause this entire thing to swoop on down, cross through my 0, and swoop on down further. And sure enough, let's plug it into GeoGebra and see what happened. This is our original graph right here. We can see that if I write it where I put a 0 in front, actually the computer's not even going to let me do it because it's the exact same thing. And that's literally the same thing right on top of it. So we changed the perspective without changing the meaning. And then within this one, we had a vertical asymptote at x equals 2, at x equals -2, and at y equals 0. So we got the full story we needed. So a couple of terms to be aware of for this section. What is a vertical asymptote? We've already figured that out. That's any time where I'm having a divide by 0 error. And as we'll see, it's a time when I have a divide by 0 error, but the 0 doesn't cancel away, it doesn't simplify. What is a slant asymptote? This is any time that the thing you approach is actually a line. So this is going to happen whenever you have something above another polynomial where this one is 1 degree bigger. So you could think of this as x over 4 compared to x over 3. You could think of this as being a whole bunch of things where it's 1 degree higher, 3x to the 4th plus 2x, still over x over 3. You're looking for when this degree is higher than this degree, because as it turns out, when you do your division, you're going to end up getting something that is linear. Something like, I don't know, maybe x plus 2, we're just doing an example here, an x plus 2 plus your extra. And as it turns out, this is a line. This is a slanting line. So a slant asymptote is when instead of approaching a line that's horizontal or vertical, you're approaching this line right here. It's the equation you get close to. And we call those slant asymptotes. But in truth, you can have any kind of asymptote. You could be getting close to a cubic. You could be getting close to a parabolic. Okay, I'll leave this for you. How do the remainders and the end behavior affect the graph? That's for you to kind of look at, observe, and then take some time and write some notes to yourself. Okay, so as a reminder, is x over x equal to 1? Let's try it with some of these values. So the first thing we could do is we could say, okay, well, negative for -2, is it going to work? -2 divided by -2 definitely is equal to 1. -1 divided by -1 definitely is equal to 1. And we might be tempted to think that that's true for all values. But if you try some of the values in between, try your fraction numbers, see if the fraction numbers upset it. No, still the same amount divided by the same amount, that's equal to 1. What about 0? 0 divided by 0, oh, so that one's undefined. But in the positives, we're going to get the exact same idea. 1/2 negative, or 1/2 positive 1 and 2 are all going to work out, where if you divide the same thing by the same thing, you're going to get 1 all the way down. Okay, so how do we graph this? Well, we would be tempted to say that this is going to be something that has a whole bunch of points that are 1 high. And some of the mistakes that I see is that we don't take this for that entire meaning, right? So we're trying to say, okay, so if I do something like -2, what if I did -1? Those are all going to be values that are 1 high. So 1 high here, 1 high here. We could imagine that this can be 1 high for the numbers in between that, and we keep going. And sometimes people say, okay, well, I did it to -1/2, so I'll plot it here and then stop. But there's nothing to say to stop. Really, the only problem happens at 0. So instead of trying to draw all the points that work, let's just draw the one point that doesn't work. And we'll put it as an open circle. So we'll do an open circle to show that it actually doesn't exist there. But everywhere else, it totally does. And if you fill it up with points, you're going to see that the line that you create is actually just a line that goes straight across, has a hole right at x equals 0. Okay, and we call these removable discontinuities. They're removable because if I took this away, if I just kind of covered it up with my thumb, if I just filled this thing in, then it would look like the perfect line. Versus above, when we had a discontinuity that I couldn't remove, like here we might want to think that I'm allowed to simplify this whole thing away. It doesn't actually work. It only works if we keep in mind the time that it wouldn't have worked. But above, when we were having a divide by 0 error, they were causing a whole bunch bigger problems. We were having things blowing up and exploding and shrinking towards the negative. Here, we're really just kind of taking a moment where I can't plot a graph. So these are holes. This is what happens if I divide by 0, but it looks like I can actually cancel it away. Because in truth, you can cancel it away everywhere except for x equals 0. So a student works through this. Let's see whether or not they actually did the right work. So the work that they did is they said, I have this function. It looks like if I was going to interpret this, the bottom stays pretty much the same. It just reorganizes. That's totally fine. That's the commutative property of multiplication. I can look at multiplication in different orders. This factors out. Let's see if they factored it correctly. So we're looking for x squared, 3. That would make this have to be an x and an x. This would have to be a what? I'm looking for things that multiply to 3 and add to -1. That'd be a -3 and -1. Oh, and that would be just fine because that would give me my -x and this would give me -3x. Okay, good. So it looks like they factored that out correctly. X minus 1 is right here and x minus 3 is the one next to it. And then it looks like they just canceled away. They just canceled these things away. Is that true? It's not true. And in fact, I pulled this picture from GeoGebra as I plotted the original one. And I don't even see a hole on GeoGebra because GeoGebra isn't going to plot the open circle. That's a logic model. That's for us mathematicians to be careful for. So even if you use a computer for some of these problems, what you have to be careful of is that the computer, graphing calculator, or even powerful computers are not going to recognize holes. That's on us to recognize. So how would we adjust this picture? Well, if this is 10, this is probably 5, this is probably 4, this is probably 3. At 3, we need to come in here, we need to draw an open circle in the graph and show that there actually would have been a gap right there.